Hi everyone, this is Aishwarya and we will be discussing the integer representation part from section 4.2. We have seen different number bases in this course, namely binary, hexadecimal, octal, and decimal. Now we will look into what does base expansion mean. Let b be an integer greater than 1, then if n is a positive integer, it can be expressed uniquely in the form of like this. Base b expansion of integer n means I can take any integer n and write it as a sum of different powers of this base b. Here, all the a's that we can see are called the coefficients, and this k is the power of b is a non-negative integer, and all the a's are also non-negative integers. And it can be written as like this. So here, this is the base b representation of the integer n, and here all the a's are the coefficients. So this is how we represent the base b expansion of n, any integer n. Let's see an example. This example is from problem set 7 and question number 7. We need to convert the binary expansion of each of these integers to a decimal expansion. So the first example is we have 1. This we have 0, 1, 2, 3, 4. We have 5 ones over here. And this is the binary representation, and we need to do a decimal expansion. So in order to convert the binary to the decimal, we first need to do the base 2 expansion. So since we have 1 5 times, we need to start with the power of 4, because the first one starts with power of 0, then 1, then 2, then 3, and then 4. And all the coefficients are 1. So it will be 1 into 2 to the power 4 plus 1 into 2 to the power 3 and so on. So this is what the solution looks like. So 1 into 2 to the power 2 plus 2 to the power 1 plus 2 to the power 0. And when we do all this addition, we get the answer as 31. This is the decimal expansion. Decimal expansion is basically what is that decimal number. Now second, we have this binary number. So here we have how many digits? 0, 1, 2, 3, 4, 5, 6, 7, 8. So we start with 1 into 2 power 8 plus 0 into 2 power 7. But since it's multiplication by 0, so we can basically skip adding it to the equation. So we have 2 power 8 plus 2 power 6, this is 5, then 2 power 4, this is 3, then 2 power 1, 2 power 2 plus 2 power 1 plus 2 power 0. So we have 2 power 8, 1 into 2 power 6, 1 into 2 power 4, 1 into 2 power 2, and 1 into 2 power 0. And when we add all these numbers, we get the decimal expansion, which is 341. Our last example is this. So here, this is the binary representation, and we need to do the same steps again to convert it to a decimal number. So here we have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So basically we add the powers of 2. The powers will be 14, 13, 12, 11, 10, 9, 8, 7, 6, 5, 4. So we'll be adding 14, 13, 11, 8 and 4. The power, these will be the power of 2's, and when we add all these numbers, we'll get the answer as 26896. So we saw conversion from binary to decimal. Now we will see conversion from decimal to any base. Here the process involves repeated division with a non-negative quotient and remainder, and we continue this process until we get the quotient as 0. So here we divide the number n repeatedly by the base b, and here we continue the division by dividing the quotient every time, and we stop this process when we get the quotient as 0. So let's see an example for this one. So here we need to convert integer 1, 2, 3 to base 8. This integer is in base 10. So let's divide 123 by 8. So here we get 8 into 10 is 80. No, then we do 8 into 15 is 120. Yeah. So here we do 8 into 15 plus 3. So we know that 3 is the remainder and Q quotient is 15. So we get this. Now we need to repeatedly divide the quotient. Here it's 15. So we divide 15 by 8, then we get 8 into 1 plus 7, which is this. So this is the base rate expansion. And then we continue dividing 1 with 8, and basically it's 8 into 0 plus 1. So this is the base 8 expansion. Now we need to combine the answer, so we go from bottom to top. So we can represent 123, which is in base 10, as 173 will be its base 8 representation. Now let's see how we can directly convert from decimal to octal or hexadecimal and vice versa. Each octal digit corresponds to a block of 3 binary digits, and each hexadecimal digit corresponds to a block of 4 binary digits. Don't get confused. We will see what this means in a minute. So we will use a table. This is the table that we will use to do our conversions. So in this table, we have decimal, hexadecimal, octal, and binary representation of numbers from 0 to 15. We have 15 because we need to use hexadecimal. So if I'm looking at a particular number in a particular base and I need to convert it to another base, then I just need to look up that number in the other base. Let's see an example. This is an example from problem set 7, question number 8. Here we need to convert the octal expansion of each of these integers to a binary expansion. So basically we need to convert an octal number to a binary number. So let's bring our table for our reference. And our first example is 572 in base 8. So we look up 5 in the octal row. We have 5 and the binary representation for 5 is 101. So for 5 we have 101. For 7 we have 111, and for 2 we have 10. So since 2 is just 2 digits, and remember that an octal should have 3 binary digit representation, so we just add a 0 before 10 here to make it 3 digit. So the final answer is 101, which is 5, 111, which is 7, and 010, which is 2. So this is our binary expansion of this digit in base 8. Our next example is 1604. Pause the video and try to do this by yourself. So here 1 in octal is also 1 in binary, but remember that we need to have 3 digits, so we add 2 zeros before 1. And then 6 can be represented as 110 in binary, 0 can be represented as 0, but remember we need to add 2 more zeros to make it 3 digits, and then 4 can be directly represented as 100. So we have 001, which is 1, 110, which is 6, 000 is 0, and 100 is 4. So this is the base 2 expansion. And note that we have 2 zeros in the front over here. So in our final answer, we can remove those 2 zeros because they won't affect our answer in conversions. Our last example is 2417. So again, we'll use the table. So from 2, we have 10. So basically it will be 010. From 4, we have 100. From 1, we have 001. And from 7, we have 111. So this is 2417 in binary. This is another example from problem set 7 and question number 9. So here we need to convert the hexadecimal numbers to binary numbers. Previously, we converted octal numbers to binary numbers. So here we bring the table for our reference, and the first example is 80E. So here we look 8 in the hexadecimal row. So we have 8 here, and then we go to the binary row and we find 8 is represented as 1000. Now 0 is represented as 0 in binary, but remember that for hexadecimal we need a 4-digit binary representation, so we write 0 4 times, and E is represented as 1110. So this number will be written as, this is 8 in binary, this is 0 in binary, and this is E in binary. So this is our entire binary representation. The second example we have is 16, base 16. So in the problem set, base 16 was not there, so I'm just assuming that it should be base 16. Now let's look up 1 in hexadecimal row and look up it in binary row. It's 1, so it will be 0001, and 6 can be written as 001. We need to add 0 in order to make it a 4-digit representation. So we have this is 1 in binary and this is 6 in binary. So this is our hexadecimal 16 to binary conversion. Next example is ABBA. So we look up A in the hexadecimal row and try to find its binary representation. So it's 10 or 1010, and for B it's 1011. So here our answer will be 1010 is A, then this is B 1011, then again B, and then we have A. So this is the binary conversion of this hexadecimal number. Now this is another example from problem set 7, question number 10. Here we need to convert this binary number to its hexadecimal expansion. Remember that we can use this table for conversions from any number system to any other number system. So now what we do is, since we want to look up this number and we want to convert it into hexadecimal, we need to group it in digits of 4. So here 1011, let's try to look up 1011 in the binary row, and it's represented as B in the hexadecimal row. So it's B, then we have 0111. So here you can ignore the 0 and just look for 111 in binary, and it's 111, and the hexadecimal representation is 7. So this is 7. And then we have 1011 again. So this and these are same. So it's again it's B. So the answer is B7B. So this can be represented as B7B in base 16. Now this brings us to the end of this video. Thank you all for watching.